Hey folks, this is the introduction to MATLAB video for MEAM 211 for the spring of 2017. I'm Michael, I'm one of the TAs, and I'll be taking you through MATLAB. So here's the table of contents of what we're going to be talking about throughout the course of this video. I fully expect that a lot of you at UPenn in your sophomore year already know quite a bit of this. I would, however, recommend that you all skip ahead and take a look at solving differential equations numerically. If all the stuff in that section of the video makes sense to you, then you probably know how to do most of the rest of it. In theory, all this stuff on YouTube should be little links on this page, and so you can use this page to jump around and find what you're looking for. Post on Piazza if you have any questions about the video, if there's anything that's unclear, and I will try to follow up with that. So the first thing you need to know is how to get MATLAB. At UPenn, we have a couple different options. You can go download it for your computer, which is what I would recommend, and give you a link here. You'll just need to have your UPenn login there. You can also use the engineering virtual labs. There's a link for that here as well. You should be able to access these from anywhere, from any computer. And then finally, you can use MATLAB Online, which gives you the same MATLAB interface you'd have locally, but in a web browser. And you use the same sort of login that you would use for the student download page. So if you go here, there will be information on how you get your login that would work here. The next thing to do is to take a look at the interface inside MATLAB. So to start off with, on the left side over here, we have the current folder you're operating in. And so this will show the files you can operate with, different types of data, whatever else. On the top up here, you have where that file location is. So if you take a look at this, I can actually go in here and I can modify that directly, or I can click in this little browse for folder, and I can look for a different place that I want to open up. It's important to note that MATLAB will only be able to run the files that you have over in this area. The next area is the command window right here in the middle. And what this does is this area allows you to type in various commands that you want to just give a try to. See, do 5 plus 5 and tells me it's 10. The next area is the workspace over here, which holds the variables that I'm currently manipulating. So if I go over into the command window and I create a new variable, call him Bob, and I say Bob equals 5, and then we can see that Bob now pops up over here. As we get to more advanced things, you'll see things like, I'll make something new, like this, where this is actually a matrix. And you can double click on the matrix over here and it shows you what it actually looks like in an Excel type view. Close that out. Eventually we'll also have script windows popping up. So if I just click new script real quick, then you can see there's a script right here. We'll talk about that some more. Up top, we're going to have various different ribbons in a similar fashion to what you see in Word and other programs. So you've got your basic, new, open, run, etc. Some things of note: this little button right here will allow you to auto format your code, which can be really handy. These buttons right here can help you with commenting, so those are also handy. You have various different types of files you can create up here. It kind of lists out what those are, and then we'll get to publishing at some point as well. And then as far as customizing your window, you can go across multiple screens and change which windows you have open, and that's all controlled via this view tab up here. The next thing to discuss is where to get help for when you're working with MATLAB. And really there are tons of resources out there for you. The first and probably best resource is the MATLAB documentation itself. To find that, you can go to mathworks.com/help/MATLAB. When you get there, one of the first things you'll see is this Getting Started link. And if you go through there, there are a bunch of videos that are probably better than this one at describing how to use MATLAB. If you really don't know what you're doing with MATLAB, I highly recommend you take the time early on in the semester to start going through some of these things. There are also various other fundamentals and whatever, but really for most things you can just type in what you're looking for. So let's say that I want to make something with some zeros. I can type that in, and maybe I know what the function is I'm looking for. I do, but I don't really know how to use it. Well, you can go into here and it's going to give you a really nice interface on exactly how to use it. as well as examples. And recently with that web browser thing, you can try it in your browser, and in theory it pops up and shows you the function working, although probably not in the browser I'm using because I'm lousy like that. Anyhow, this gives you a lot of wonderful information, and it's easy to keep it up and look around. Another great option is to just use the internet. So if you want to look for, like, what does a dot operator do? Because we talked about that, but you don't really know what we were talking about. Well, Stack Overflow is great. And here you'll see someone ask a question, and there's an answer down here, and you can see people will comment on the answer and go through it. And these exist for essentially any programming language you'll ever need. So I highly recommend using that resource. We also have a class, Piazza, and I recommend you use that as well. Piazza is great because you guys can answer each other's questions, which helps all y'all learn. So we, the TAs, will be going through Piazza, but we're going to give you all a chance to answer any of the questions first, and then if it falls through the cracks, we'll come back and answer it. It'd be better if y'all are just answering it all and we just get to say good job. But the way that works is essentially you click New Post up here on the top, and then you can come in here and you can type, a summary of, let's say, how do you multiply matrices, which you should be able to answer online. You can select which of the questions, which the problem sets it belongs to. You can post the entire class or to just the instructors. Really, if it's a general question like this, you can go straight to the entire class. If it's something more specific where you're having a problem with just your stuff, and you're concerned about there being, whether it's appropriate for you to let the whole class know, absolutely just post to the instructors. And then, yeah, so you can ask questions there. Everybody else can collaborate on them. So let's see if I can pull up an example of what this might look like for another class. So here's another class that was using Piazza that I took, where you can see someone asked a question, the instructor gave an answer. Here's an even cooler one because you can see that student asked a question, student gave an answer, another student gave an answer, instructor gave an answer. In this one, somebody asked a question, student gave an answer, and the instructor endorsed it, so that's great as well. Some other things you can do, we have office hours, many hours a week. Absolutely come into office hours and ask us questions. We encourage you to do that. And then another thing to just throw out there, a technique that's used a lot in programming is called the rubber duck method, where you sit at your desk with a rubber duck. And when you have a question, the first thing you do is you ask the rubber duck your question. And a lot of times you'll find that the rubber duck can answer your question for you. And even if it can't, then just by formulating the question, so you had to verbalize it out loud, so I actually want you to ask the rubber duck out loud, that helps you ask the question more coherently to somebody else, and you can get an answer more effectively. Next up, let's take a look at some of the kinds of manipulations we can do in MATLAB. Let's start off by cleaning up our workspace. So you can see that here in the command window, I've got a bunch of junk there, and then I also have a bunch of stuff up here in my workspace. And I don't really want that there right now, so let's get rid of it. To clear out my command window, I'm going to type in CLC, which is like clear local command window or something like that, and you can see it's clear. To get rid of my workspace, I can just type in clear, and I've cleared that out. So now I have a clean place to work. So let's start off with creating a variable. Let's say I have Bob. I can set Bob to be a number. I can set Bob to be a string of some sort. Right? I can also set Bob to be a Boolean value, which can be not that, false, or true. And I want to highlight a couple things real quick that just popped up. So the first one is when I typed in some sort of garbage up here, I got some red text telling me that something was wrong. So that's really helpful. Pay attention to that red text. It's going to help you out. I also want to point out that some things up here turn into links, and so you can click on those, and that'll bring you to help somewhere, which can be useful if you don't know exactly what they mean. So let's try to do some addition. Let's say that I want Bob to be equal to 15 plus 10. Then you can see that's 25. I note that this is printing out something down here. Every time I type in, I get this result down here. I can get rid of that by suppressing my output. And I suppress my output by putting in a semicolon like that. So now you can see that the value is up in the workspace. And just to prove that I actually did that, let me change that to another value. And you can see that it changed up in the workspace. Workspace being up here. But it didn't have to print everything out. So that can make things a lot cleaner. When you're writing large blocks of code, you're generally going to want to suppress everything. You should leave things unsuppressed only for debugging purposes. When you're working in the command window, it's not a big deal. So we can also do subtraction, so something like that, and we can see that works out just fine. And then we can also do some stuff with booleans. So let's take a look at doing an Boolean comparison. So let's say that I have false is equal to false. And so the way that Boolean comparisons work is you can have double equals, you have x, which is this, so it's going to be say that it is in fact false is equal to false. I can also do a not equals with an exclamation point. So false is not equal to true. Apparently not. How about a tilde? Hey, there we go. So tilde equals is not equals in MATLAB. And we can do this with variables as well. So if I say Bob is equal to true, Sue is equal to false, and I can say Bob is equal to Sue. Had a problem because there was no space there, I guess. Okay. And that's what we would expect. And if we do the not equals, also what we would expect. But that's not terribly useful because these are all trues and falses already. We can compare anything though. So let's say that I have 5 is equal to 5. That's true. So let's say Bob equals 5, Sue equals 25 divided by 4. You see division works as well. And I say Bob is equal to Sue. It's false. And this is going to come in a lot in some of the other programming. There are places where you'll really need Boolean comparisons. We can also do ORs. So an OR is going to take in this logical concept of whether either or whether a series of options is true. So to illustrate that, I can have a false, and then OR is going to be this upward little line thing. It's right above the backslash, or it is the backslash with a shift on it, and then true. And we see that that came back as true. And I could have, a number of different things I could be comparing in here, like 5 is equal to 5. Well, let's make that false so we can see something interesting. And then, 4 is equal to 4. And so that comes back as true, even though the first one would be false. We also have and is going to be an ampersand like that. And so let's give that a try as well. So let's say that we come up here and we change this. Real quickly, the way that I'm doing that is I'm pressing the up arrow. So I can press the up arrow and I can scroll through my history. It can make it a lot quicker to go through what I've been working on in the past. So if I change this to an ampersand, you see that's a false. And that makes sense because the first item is not true, even though the second one is. Now if I change the first one to be true, you can see that came back as a logical true. Haven't mentioned it yet. Should be clear. Ones are trues, zeros are falses. You also notice that I'm using parentheses. In the same way you do in math, you can use parentheses in here to do groupings. So I can do something like 5 plus 5 times 4. And I'll get rid of that first one. And you see that comes out as you would expect, which would of course be different than if I were to do this because of order operations. So next up is the thing that really makes it the meat of MATLAB. MATLAB stands for Matrix Laboratory, and it excels at doing matrix manipulation. If you have an opportunity to use matrices to do what you're trying to do in MATLAB, you should. It will always run best that way. And so the first thing to talk about when we look at matrices is how they're indexed. MATLAB uses 1-based indexing, which means the lowest number in your index is 1. And you can see here that it indexes dimensions in this way to where the first number, if you're doing a two-dimensional matrix, represents the rows, and the second number represents the columns. And so you can see how that is illustrated here, and that continues on into multiple dimensions where you can have arbitrary dimension matrices as long as they're rectangular. So to give you an example of what that looks like, if we had this matrix right here, you could index into it using this notation, where you put the index you want in parentheses. And here we're looking at the second row, first column, and that leads us to 23. We can also index using this unwrapping method where MATLAB will go down each of the columns in sequence. So wrapping down like this and then coming down like this. So it kind of goes like that, right? And so that is using a single number on a multidimensional matrix. So this would be 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and onward. And so we can index it using 2. Similarly, if we wanted to get to this 13 over here, then we could do that by typing in A of 3, 3, because we're looking at column 3 and row 3, or 13, because if we looked at it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That leads the value we were looking for. So let's first take a look at how to manually create some matrices. So if I want my matrix to be equal to, let's say, 4, 5, 6, then I can do that. I can also use some various space creation type things. So I won't even store them anywhere, but I can do, I want a matrix from 5 to 9, and it'll create that for me in a logical way, stepping over by 1. But let's say I wanted that to step over by 0.1. Then I can put my spacing operator in there, and that was too much to demonstrate that with. Let's say I just want it to go over by 0.5. So you can see that here, I went over by step size 0.5, and that worked just fine. Let's say that I want to create a matrix between 1 and 2, and I know that I want it to have 10 steps, and I don't want to try to think about the math of how to do that. I can use linspace, which is going to be a linear space, to do that. And here you can see that I actually created that. It's going from 1 to 2 with 10 samples. I can also do this with exponential type things. And you know what? I honestly don't even remember how to do that, but I know that it's going to be similar to linspace. So if I press F1 inside the linspace, then I can see that, and it's, here we go, log space. So I can go ahead and use log space. And it says it's essentially the same thing, but if I remember correctly, the operators aren't quite the same. So it's doing the powers of 10. So let's say that I wanted to go from 1, which would be 10 to the 0th, to 100, to 10 to the 2nd. And let's say that I wanted just 20 samples. Then you can see that it generated that. So initially the samples are stepping over by a relatively small amount, 10 to 11.2 to 12.7. Those are small sample jumps. All the way at the end, we're going 88 to 100, which is a relatively large sample jump. So that can be cool if you know you need to sample specifically in one area. So let's say I want to make a matrix that has multiple dimensions, not just, this is just a single dimension. What if I want to go into a second row? Well, I do that with a semicolon. So I go 4, 5, 6, and there we go, I'm in a second row. And I can keep doing that. And there you go. You'll also see some people, instead of using commas, they'll use spaces, which is totally valid. I find that much harder to read personally. But if that's what you like, do what you like. And there you go, that works as well. So now let's go ahead and try out some matrix work in the MATLAB window. So let's say that I want, to make my matrix. And I just know I want a bunch of zeros. And let's say I want a square matrix of size 4. And I can create that real easily. So earlier I showed you how you can find some help by going online. Another thing you can do is you can go onto the function. So you have my cursor's on the function, and press the F1 key on your keyboard. And you see it right away, it opens up some information about the function. I can see how it works. If I wanted to, I can also open this in the help browser, which is a little more full-featured. Press F1 again in theory to make that go away. Nope. Press escape. Escape makes it go away. Okay. So I've got a bunch of zeros. Now let's say I wanted that to not be of size, 4 by 4. Well, if I pay attention in here, I can use this zeros of size, it says Z1, bunch of dots ZN. So that's telling me that I can essentially define the different dimensions. So I can say the other dimension I want it to be 2. And I could even go into more dimensions. So now I've got it's a little bit harder to visualize, but I've got 3 dimensions right here. And if you look up into the workspace up here, you can see that it's a 4 by 2 by 5. So those are the different dimensions I just created, which corresponds to what I typed in. Great. So some other ones that are useful are you can do the ones. So I'll get rid of one of those dimensions. So I've got some ones, and there are a whole mess of these that you can play around with. So let's say that I would just create some random ones. So we can use rand for that. I'll make a 4 by 4 there, and I'll make another 4 by 4. Okay, now we can multiply these together, and you can see we get a result. And you can see it's different if I go in the other direction, which makes sense because this is matrix multiplication. So remind yourself about the differences between matrix multiplication and traditional multiplication. They're totally different. But let's say that instead what I wanted to do is I wanted to multiply each individual element in Bob and Sue together. So I wanted to multiply, if we go up a little bit, I want to multiply this first element right here with this first element right here, and equally this last element right here with this last element right here, and I just want to do each one element by element. Well, then I'm going to do that by using a dot. So if I do Bob dot asterisk Sue, then that's what it'll do. And now in theory, because standard multiplication is commutative, I can do that in either direction, and I should get the same values. You can see I do. That's really useful. So now let's see what happens if I were to do something like this, where I've got now a non-square, but still obviously rectangular matrix, and I'll create another one that's rectangular in the other direction. Right? So they're both, one's 2 by 4, one's 4 by 2. Now you can see if I do that, that works, because Sue times Bob, the way the dimensions are set up, is valid underneath matrix multiplication. But now if I go in the other way, it also works, but you can see I get a different dimension back out. So now if I were to change Bob to be a non-compatible dimension, like that, I did that wrong. No, that's good. Then you can see in one direction it's going to work, but in the other direction it's going to give me an error. And so it's saying that the dimensions must agree, and so that means that when you did matrix multiplication, it just doesn't make sense. So yeah. So let's also take a look at some indexing. So I'll pull back up Bob so you can see it. So if I just want that first element, I can just type in 1. It would be equivalent to type in 1, comma 1, because it's a two-dimensional matrix. If I want the element down here, there's 0.6797, that's 4 down. So I should be able to type in 4, comma 1, or just 4, because remember it'll go down. Now if I were to type in 1, comma 4, then that would put me off the edge of the matrix. So we should get an error, and indeed we do. And so that's useful. Let's take a look at Bob again. So let's say that I want these 3 values right here. It's 0.7547, 0.27, 0.6797. Then I can do that as well. So I'll do that using a range. So ranges are done using colons. So I'll go from 2 to 1, 2, 3, 4, right? If I remember that correctly. And let's see what that gives me. And you see that that gave me exactly what I was expecting. I can also do to where I get the whole column or row. So if it, I haven't quite made it clear yet, but this first item is taking the column, or sorry, the rows down, and the second element is selecting the column. I can select all the rows by just doing an unended colon like this. You can see it selects all of them. I can also do something where I go to the end. So I can do 2 colon end, and it'll work just fine. I can also index off of the end by using a negative value. So I can do n minus 1. And that's also useful. Now if I make Bob a little bit more substantial, then I can do some 2 dimensions as well. So I can do, let's do 2 to 4, comma 1 to 3, and you can see I can get a chunk of it out. I can also use this to do reassignment into the matrix. So if I take that section, I can assign it to have a new set of values. So let's say I just want it to all be 1s in that area. And that's a 3 by 3, so I'll make it 1s of 3. Well, let me make it 1s of 2 first, and let's see what happens. You can see it breaks because the dimensions don't match up, which is what we'd expect, so that's great. Now when they do a match up, you can see that what's done is it's gone and put in this block of 1s where I was indexing from. So 2 to 4, so that's 2 to 4 right there, and then 1 to 3 coming across. So that's handy as well. And I think that is most of the basics of matrices. One of the things to note is that there are a lot of ways you can do fancy math on each element of the matrix, on groups of elements in the matrix. And if you find yourself needing that, I highly recommend the MATLAB documentation. The next thing I want to talk about are structs and cell arrays. And the reason to talk about these is because they're so often overlooked by people who are just learning MATLAB. And in the case of structs, they're a really easy way to store data, and in the case of cell arrays, they're really powerful and very confusing. So I'll definitely make mistakes as I'm going through this. So let's start off with structs. So let's say that I've got something like a student that I want to represent. A student can have various different attributes. Let's say a student has a grade, right? And so let's say that the student's grade is a 95. A student can have other attributes too, like a year. Let's say the student's year is sophomore. And what else can a student have? A student can also have a gender. So let's say that's female. And so what you can see is that I'm building up this representation of this student. And so this is a really powerful way to be able to access stuff, because now I can go back into that student and I can access their year and get this out, and it's really easy to read for a human. So although I could store all this information in a more, well, I'll show you in a moment, in a cell array, this way makes it really, really easy. And you can also start to make arrays of these. So I could make, let's make Sarah equals student. So we'll store student Sarah, and we'll say that Sarah's name equals Sarah, right? And let's make another one. We'll say Bob equals student. We need to change Bob's gender to be male, and let's give Bob a different grade. Okay, so now we can see we've got, oh, we need to give Bob a name as well. So we've got Bob there, we've got Sarah there. Now I can make a student's matrix that is equal to, has Bob and Sarah in it. And so now it's showing you have this struct array. And so if we go to look at students and the first element, I did that wrong. Then we can see that that one's Bob, and the next one is Sarah. And so that's it's a great way to organize data, but can become computationally expensive, I would note. This actually ends up becoming the basis for how you do classes in MATLAB and how you can kind of begin to build those structures up. So now let's talk about cell arrays. So cell arrays are used to hold data that's not numerical. So if you notice when I was doing matrices, everything we touched was numerical. Cell arrays work differently, so I can hold anything in them. So let's say I've got my cell array, and I'm going to denote that with these curly braces as opposed to the square braces we were using for matrices. And so I can put whatever I want in here. I can put some strings, some numbers, maybe a Boolean value, and close that up. And now I've got the cell array. And you see inside of each cell it's got a thing. All right, so in the first one it's got a string, and a string is really underneath the hood an array of characters, so it's just that. In the second cell it's got the number I created, but it turned it into a matrix. And in the third array it turned the false into a 0, because that's what false is represented as, and then turned that into a matrix as well. So now the fun part. When you start indexing into cell arrays, it's a little bit different than other systems. Because you can see here that when I indexed in using my traditional parentheses, I actually got a cell array back, which sometimes might be what you want. Now, if you use the braces to index in, then you get the actual value back. And so this becomes really powerful. I can also store other stuff. So let's say that I want to add on to the cell array some sort of matrix at the end, right? Then I can do, let's see if I do this right. Before I run it and store it in there, let me just do it like this. Let's say I have a ones matrix again. Then that seems to have worked, so I'll store that in my cell array. As you can see, some of this stuff is a little challenging, at least for me to remember, but you can always try it out. You're working on a computer, so mistakes are just fine. It's all right to make them. And so then I can go into my cell array and I can index the fourth element in there, and I get back my ones matrix. So hopefully the power of this is apparent, that you can store a lot of different types of data in these types of structures. So next up, we're going to talk about how to make scripts. Essentially, you're going to want to use a script anytime you have blocks of code that you're running that you want to be able to rerun. So the command window is great for trying something out, doing a simple calculation like you would in a calculator, but for anything more meaningful, the first thing you're going to turn to is a script. So to make a script, you're going to go over to the Home tab up here, and you're going to click New Script, or you can press down on the little new thing, and there will be some script options there. So create a new script. So I've got it right here. First thing you want to do is save it, and I will save it into a place for this class. Here, give it a more meaningful name. It has to end with .m because MATLAB uses M files, so we'll just call it and they have some forbidden characters in here. It'll give you an error if they're no good. For this class, any scripts we make, we're going to want you to put comments in at the top with your name and your section. So you put a comment in by putting a percent symbol, and then put my name, and I'll just put that I'm an instructor. So the first thing I want to show you in scripts is you can put some code on in here. So if I have, some variable equals 5, and here's where you really want to use that suppression. So I'll suppress it, and then equals, let's say, some underscore variable divided by other. And I'll leave that one unsuppressed. Now what I can do is I can run this, and if I hover over run, you'll see that there's also a keyboard shortcut F5, so I'll just press F5. And you can see it's going to say that I'm not currently where this script is. So if you look over on my current folder window over here, I'm not where I just saved that thing. So all I'm going to want to do is go ahead and change the folder to where it is. You can see the folder's changed on the left side, and now it can run and I get some value out. This is kind of contrived, but you can imagine this gets a lot bigger. So the next thing to show you in here is I can make these blocks, and blocks are useful because you can run independent inside of each one. So I'll make a block with a double percent symbol followed by some text. So I'll call this one like setup. So it'll be calculation. And let's say I go ahead and I suppress that. I want to show you right here, if you look at this, the equal sign has a little underline. And up here, you can see that there's like a little orange block telling me there's something up. That's because MATLAB prefers that I suppress things. So if I go ahead and I suppress that, then you can see that all those symbols will disappear. I can also do things like just make something that's completely an error. So let's say I do that. In theory, it should notice that that's an error. And you can see again, the little equal sign has a problem. There's this little thing over here indicating what line the error is on, and again up here. And if I highlight over that equal sign, then it should, in theory, tell me what's wrong. So it says, oh, it's got the semicolon. Let's see if I fix that if it goes away. Oh well, let's run it. And now we get an error down here. It didn't pop up there. Sometimes it catches errors, sometimes it doesn't. The difference between compile time and runtime errors, but let's go ahead and clear that stuff out. So maybe I'll add another section that's something like print, and I can do, see if I have that right. So this is a way that you can print out your values. It's useful. Essentially I'm saying that I expect to get a float back, so I'm using this %f. That %f will be a placeholder for the value, and the text will be what it is. And now I can give it a thing res. And in theory, now if I run the script, and you can see down at the bottom of the command window that it actually printed stuff out. Notice that it didn't add a new line, so I'm going to manually add that in. I'll give it another try, and now it does what I would want it to do. Yeah, so now let's show you what these blocks allow me to do. So if I click up in this first block inside setup, you can see it turns yellow, and if I, instead of pressing F5, I hit Control Enter, then it will just run that block. And I can prove to you that worked by clearing out my workspace. So pay attention to the workspace up here. When I run this setup, so with Control Enter again, you can see that it actually runs those operations. I can now run the calculation, and you can see that calculation ran, and I can run the print. Now, this is great because it allows you to break up your individual elements of code and really see what's going on by going step by step through there. And that's really useful. So that's that. The next thing is going to be publishing. So let's say that I do something a little more advanced. Let's add in a little plotting in here. So I'll just make some random values. And I will make that a 1 by 100, as we showed earlier. And I'll make some values for t, which we'll just make and I can right now hit Control Enter and see if those do what I expected them to do. They both make 1 by 100 doubles. Again, you can see that right up here. And so then what I want to do is I want to just do some quick plotting. So I'll just type in plot t, rand underscore vals, and let's see what that does for me. All right, great. I made some sort of little plot that's pretty useless. So what I wanted to show you is that now I can publish these. So this publish button right here will create a nice little output. I can just press that. It'll run the document, however long that takes. And you'll see it going through all of its individual steps. And then it'll give you an output that's really nice for submitting. So anytime that you're giving us MATLAB stuff, we'll expect you to submit it published if it's a final script. So we can see the output and see the code. This is another place you'll see the power of blocks, because you can see right here that it takes each block, and then whatever the outputs are for that particular block, those go in underneath that code. And then it also brings all your graphics nicely. And so this is actually an HTML file. You can see where it's saved up here. But you might not want an HTML file, so you can hit Edit Publishing options. Come in here, change this HTML to be whatever you want. PDFs are generally what you'll use to submit. You can close that, and you can publish it again. And there are also other settings in there you can play around with as well to see what they do. Give that a second. And you can see that now it opens up just a PDF reader wherever you've got one. And now you have a nice little PDF. Has a table of contents at the top and everything. You can click and go to where I want to go. And this is great for submitting work. The next thing I want to show you with scripts is that you can also make these interactive type scripts. So just hit down the new little arrow. There are also different types of scripts. Hit live script. And these will work a little bit more like a workbook, which can be really handy for if you're just playing around with some calculations. And so if I do this, so let's just see how do 5 plus 6. I hit, I think I hit Control Enter to run again. Yep, so Control Enter, and you can see it put a result over there. Up here you can click on Live Editor and you can add new sections. And then you can also, somewhere in here, add text. So here if you go into Insert, you can type text, and then you can have right, and so now I can have notes in here. I can add another section break and change that to be code. You know, and do a little random matrix and store it somewhere. I can run that. And so you see it gives you all this nice little output over here. Little things you can click on, and you can also tell it to go inline instead of on the side using these little buttons up here. This can be kind of handy. This can also be published out, although it uses a slightly different mechanism. So you go, maybe it's underneath the Live Editor, you go Save, Export to PDF right here. And you can see that it'll just save some PDF right there. And that PDF has been saved over here. And open that up. And I couldn't open it. Who knows why. Okay, but that should generally work. So that is it for making scripts. So the next thing to discuss is how to make functions. Whereas scripts are useful for taking blocks of code that are kind of preset, you're going to want to run over and over again, maybe taking in some data from a file. Functions are useful for situations where you're going to want to be able to put data in and get something back out in a cohesive fashion and be able to reuse that over and over. So we'll just create a new blank M file up here, and we'll use as an example making a factorial. So there is actually a built-in factorial function, which is what you'd actually want to use. So anytime you go to build something new, make sure MATLAB doesn't have it already. But just for demonstration, we'll make a factorial thing. So I'll name it something that's not factorial, because that would clobber the MATLAB one. And then I'll say function. I'll give it the outputs, and I'll just call that out. Equals well, I gotta have the same name as my function, or as my file name. And then it's gonna take in just n, right? Because that's all you need. And then at the end of your function, you have to have an end. So I'll go ahead and throw that down there. Now it's pitching a fit right now because these things aren't used yet. That's all right, because we're going to go ahead and use them. So we know that a factorial, for a factorial, that the function looks something like this. It's factorial of n equals n times factorial right? And so we'll just essentially implement that right here. So that out equals n times, and we'll use the same function we're writing. This is called recursion, because it's going to recursively call itself. It'll kind of keep going all the way until something doesn't call itself again. If it infinitely does that, then that'd be an error. We'll say n minus 1, we'll have that loop. Now this would break because this function would just keep calling itself until the computer ran out of memory, or until MATLAB reaches memory limit. That's because we've forgotten something here, and that's that we know that we'll create an if statement. So I showed you some Boolean operators earlier. I'll show you how to actually use them now. So if n is equal to 0, then we know that the result is going to be 1. And then the equation holds for everything else, so we'll put an else there. Let's complain that I didn't express that. And then we put an end, and the ifs. Okay. Here's this white space. I can show you that little formatting button I showed you earlier. So here, if I press that, we'll select everything, and then press it. You can see it reformats everything to whatever the MATLAB syntax likes. So now, let's go ahead and try running that. So I saved the function, type in my underscore factorial. Let's just do something easy like 3, and it gives back 6. 1 gives back 1. All right, so what if we had made something intentionally wrong here? What if we said that the output here is 2? And we can run it again. And you can see we're still getting values out, and that's fine. But what if I wanted to come in and see where these problems are occurring? Well, I can use breakpoints for that. So over here on the left side, you have these little dashes. I can click on one of those dashes, and then now, if I run my function, you can see this little green arrow pops up, and I'm stopped there. So if you look inside the workspace over here, we see that n is 9, which is the first thing factorial is being called with. And it's going to check if n equals 0. So I can use these little buttons up here, or these ones up here, or I can use the keyboard shortcuts to step through. So I'm going to go ahead and step in, and it goes to the next place. So n wasn't equal to 0. It's going to run it and keep going, and you can see it comes back into the function. It's called it again. And I can keep going through like this, and this is a really useful way to be able to see what is happening. So I'll go ahead and quit debugging. And then I can get rid of my breakpoint by clicking right there. If I have a lot of breakpoints, I can click on the breakpoint thing and select clear all. I can also use this this pause on errors right here, which can be really useful. So let's say that I just intentionally put an error in here if n is equal to 2. I'll do again, just making some sort of nonsense here. Notice I'm having to end my if statements with these end clauses again. Some other languages use braces, MATLAB just uses ends. So now if I run this, I'll come down here and I'll run the function. You can see there was an error, and I actually am now stopped at the point where that error occurs. So it's another great way to help you find your errors. I also want to point out that down here in the error printouts, it's telling you exactly what line the error is occurred at. And so you can actually click that line and it'll take your cursor there. Also useful. I'll go ahead and quit debugging again. Okay, so that's the basics of functions. The next thing I take a look at is this idea of using subfunctions. So let's say I create a new thing that's just, I'll just do random plots. So I'll just tell it to make some random plots. This function, it has no outputs, so I'm going to put empty braces. And then give it the same name as the file name. And we'll just say that all we want to take in is the number of plots to make. And now what I need to do is I need to actually go ahead and do this plotting some number of times. So I'll show you how to do a for loop. And so for loops work in this way. You have a variable, I'll call it I, it's a standard index variable. IDX is used a lot as well. And then I'm going to give it a matrix to iterate over. So the traditional way to do this is I can use something like 1 to n, because as we know, 1 to n comes like that. I'm sorry, it's not going to work down there because there's no n. But so you see it has something like that. I think it's going to tell me that I actually don't need the brackets because we're in a for loop, so I'll get rid of those, put an end in there. And then just to show you how you can do a subfunction, I'll do a separate function down here in this file called make a plot. And it won't have any inputs at all. I'll end that as well. Notice this other function up here is ended as well. And this make random plot will create a new figure. So if you already have a figure open, so if I do this plot right here, right, and take a look at that, and then I do another plot with something else, you'll notice it's hard to see, but let's do that should be clear. So now I've got this, clean little sine plot, and then now I plot something else. You can see that the prior plot is gone. If I create a new figure, then I'll get that new figure set up, and then now you'll notice that I actually have both plots preserved, and they increment as we go. So we will go ahead and create a new figure. and then I will just plot something, doesn't even matter what. I'll just do 1, 100, just some random values, and that'll be fine. So now in here I can do I can just call that function, and in theory I can now use this. So if I do want to make 2 random plots, you can see it went ahead and made 2 random plots. But let's go ahead and let's use the debugger to step through and see what's actually happening. So I'll set a breakpoint up front, and I will run the random plots, and then we can go ahead and step on in through there. So we're in the first element. If you keep an eye on the values over here in the workspace, that'd be good. So I'll continue to step in, and you can see that now we have actually jumped down here into the make random plot. And so I will keep on stepping. You can see that it, oh my, what have I done? Okay, so it made the new figure, now it plotted it, and now we've gone too far. Let's step out. So we're back here, we can step over that. So the idea of step in is it's going to go into the function. Step just kind of runs over it, and step out goes back out, because I don't really want to see what's going on inside plotting. And you see it now, it's gone back. The index is ready to increment. It should have incremented. Oh, there it goes. I guess we hadn't run through it yet. Okay, so now the index is incremented, and we're going to go on and make the next one. And because n was 2, that should be the end of the increments we need to do, and so the function is going to exit. And now we're done. And so that kind of gives you a quick overview of how functions work. Now I want to highlight that although you saw that I can use random plots from outside, I should not be able to use make random plot. See, it's going to say it's undefined, because the way that this is going to work is it's going to go look for a file that has that title, and it's not going to find it. So you can only use sub-functions inside the file in which they're defined. But if you only need them in one place, they can be a nice way to clean up your code. The final thing to talk about here is how to do documentation on your functions. So these functions are short and should be easy to understand, but it's still good practice to add some sort of documentation on here. And there are formal ways that MATLAB likes you to do this that allow you to use the help and everything really well. I'll leave it up to you to go look up how to do that exactly. But some basic things you'll always want to have, you know, what your arguments are. So n is the number of plots to make. Right, and so now the idea is that anybody else who comes through here can easily see what's going on. So we talked a little bit about plotting in the functions section, but let's go into it a little bit more. Start off with and create a new script, and I'll just save that and call it plotting example. Okay. So the first thing when you're plotting is that let's say you've got a bunch of plots open. I'll just do that a few times. And so now if you look at it, I've got a few figures that are open here. I don't want to get rid of those. So the first thing to see is you can use close all. That's going to close all the figures, and now there are no figures open. So that's handy. So at the top of my function, I'm going to put close all. I also want to get rid of all the stuff over my workspace, so I'm going to put clear all. Okay. So let's say that I want to plot a sine curve, which I did a little bit briefly earlier. So the first thing I'm going to do is I'm going to create so one of the things to understand about MATLAB is that MATLAB is really not designed to be symbolic. There is a sim toolbox or symbolic toolbox, but it's really made to be numerical. So when I do something like plotting a sine wave, I'm going to be plotting samples calculated along sine, plotted close enough that you can't see all the little lines. So let's take a look at what that looks like. So I'll start off by making a thing for the values I'll put into sine. I think those go from negative pi to, well, make it 2 pi. all the way to 2 pi. And let's say that I create a really small step size of 10 to start off with. All right. And then I'll make my values. I'll just take sine and I'll pass in that entire, what is a matrix now, to that. So if I go ahead and I run this by pressing F5, then what you'll see is that T over here is actually a matrix. And what I passed into that into sine was a matrix, and sine knows how to operate. It's going to do an element-wise operation on each of those individual things. So now what I can do is I can go ahead and I can plot the x values, which will be t, and the y values, which in this case is vals. And let's see what comes out. And so you can see that's really, really rough. And that's because the step size is so big. It's interpolating a long distance. So I get rid of that, and I now make the step size much smaller by creating many more samples. We'll do 100 samples time. And plot it again. Now you can see that the sine is actually relatively smooth. So that's handy. What if I want to plot a second thing? Well, say I want to plot cosine. Then what I can do is I can create a new figure, and I can do the same sort of thing. So I'll plot t, and this time I'll just put the cosine right in here. Cosine of t. And now if I run that, then in theory, I now have two figures, one for sine and one for cosine. But there's no way for you to know which one of these is which just at a glance, right? You have to actually focus on what's there. So one of the things we're going to expect you to do is to add titles to everything. So I can add a title by coming here like this and putting sine. Right, and now if I run it, then you'll see that they each have a useful little title. You can also add axes. So I believe it's x-axis or something like that. I can do time, let's say in seconds, and let's just say, well, let's see if that's right first. So I pressed F1 to see if you can find something called axes, and that's not the right thing. I don't remember how to do axes actually. That's okay. We'll go into online, do MATLAB. I'm sure it'll come right up. X label. And so you see this again, the internet's just your friend for this sort of stuff. Now I know what to do. They even have examples down here on how to do it. Good enough. Do it for the Y as well, which I assume has the same syntax. And let's say that this is some sort of distance in meters. Now if I run it, take a look at the sine plot, you can see that it actually has those labels cleanly placed onto the graph, and so that's really nice. Now again, if I go ahead and I publish these, I'm going to change publishing back to being the HTML version because it seems to run a little bit faster. Oh, it's already there. Great. Go ahead and publish. And you'll see that these things all carry through and you get these nice little graphs. While it's doing that, oh, there it goes. So now you can see that I've got these nice little plots, and you could easily turn this in, throw a comment with your name and section at the top, of course. So the next thing to do is to do some subplots. So the idea of a subplot is that you're going to have multiple plot windows essentially in one place. So the way that that looks from a documentation perspective, we type in subplot. I pressed the wrong thing. Alright, so wait for that to load. So it's gonna, the first two values are where in the grid you want to be. I'm sorry. First two values are defining a grid to do. So you can see here they do 2, 2, so it's a 2 by 2 grid. Here they just want, so 2 rows and 1 column, so it's 2, 1. And then the final number is your position. So if you look here, it goes across like this. So you have, this is 1, 2, 3, and then 4. So let's take our same sine and cosine and let's put them into a subplot. So we'll make a new figure, and we'll tell that it's a subplot, and let's give it 2 rows and 1 column. In the first element, we will put the one that we had for sine. We'll give that a title of sine. And then in the second position, we have to give it the same number of rows and columns. Alright, now I'm going to hit Control Enter to just run this one section. So we already have the t and values defined, and you can see that now we have this nice little plot right here. And you can get a lot fancier with this, where they don't have to be symmetrical, to where you can have like one big plot on the bottom and 2 small ones on the top and other things like that. I leave that up to you to figure out how to do that. The next thing we might want to do is be able to plot multiple things on one axis. And for that we're going to use hold. And so the way that's going to work is I'll create a new figure. Actually, let me just go edit the basic plotting, it might be a little bit easier. So I'll get rid of this figure right here, so I won't create a new figure in the middle. So we're plotting the sine, and I'm going to just type in hold on. And what that's going to do is it's going to keep the existing figure available to plot on without erasing what's already there. And then once I'm done plotting, I'll type hold off. I'm going to get rid of this title, and I'll just change that title up there. And let's just run this one section. And I must have something open somewhere else, so I'll just go ahead and close all that. And I'm not quite sure what's going on. This statement is incomplete. So same as an error on line 29. Yeah, I had some junk down here I didn't delete. Let's get rid of that. Now I should be good to go. Great, so now you can see both sine and cosine, but you don't really know which one's which. So the next thing to talk about is adding in a legend. So I can add in a legend by putting in, I want to say it's a cell array of the strings I'm interested in. So the first one would be sine. Actually, you might not need this already. I think you can actually just do a list, just like a straight, no matrix or anything. So I'll do that. Let's see if that works. And sure enough, you can see that the blue one was sine and the red one was cosine. That nice little legends popped up there. You can also do things about changing the position of that. You can also change the colors of everything, change the styles. So if I want to change this plot of cosine to look a little bit different, with the legend, it's printing out in the order you plotted. So here I plotted the sine first and then the cosine, so I put sine and then cosine in the legend. Anyhow, so let's say I want to change this to be red with dashes and dots or something like that. I think it's something like that. And then now you can see it has dashes and dots. How do you know how to do these sorts of things? Well, you go back online, you type in plot, you go to 2D line plot, and then somewhere down here it's going to say line spec. So if I click on line spec, it'll take me to another page where it details out all the different options for lines. And so that can be super handy to take a look at. It gives you a lot of customization. And then for color, you can go even beyond this using RGBD definitions directly. And so if you come down here, it shows you how to do more direct color specifications. And so that is the basics of plotting. There's a lot more you can do. You can go into multiple dimensions with your plotting, but I'll leave that to when you need it. I want to real quickly show you that MATLAB can be used to solve systems of linear equations. So as you know, any system of linear equations can be represented as a matrix equation, generally denoted by this AX equals B right here. And so MATLAB lets you use the backslash to solve those sorts of functions. So we can go ahead and just take something that they're doing here. We can pop that straight into our MATLAB command window. We can see it gives us a result back. And we can start to, change these to be something else as well. So we could do A is random of 3. And you'd obviously be taking some sort of meaningful mathematical values here. And then we can try and see if that happens to have a solution. I don't know if it will. It does. Great. And yeah, this can be a powerful tool when you're doing some math. Rather than sitting there and manually going through, you can now use MATLAB to solve your equations. So next, let's try something a little more interesting. We're going to try to use MATLAB to solve the ordinary differential equations that govern a bouncing ball. And so we'll just look at this in one dimension, just a ball bouncing down, hitting the ground, bouncing straight back up, down, back up, right? And so for the equations of this, well, let's start off with saying we're going to define this direction as x and time is t. And so the primary equation for this is that the acceleration is going to be, we'll take this to be a really ideal case. And so that's just going to be the gravity, negative gravity, right? And then we know there's a special thing that happens right here at contact, which is that at contact, the velocity, just dx over dt, is going to be equal to essentially the absolute value of the velocity at the prior time step. So we'll call that t minus 1, right? And if we want to make this a little more realistic, we're ignoring air resistance, but let's at least take into effect a coefficient of restitution, and let's call that times some k, right? And so essentially each time it bounces, it's going to bounce less and less up. So when we look at this, MATLAB can't handle second order differential equations directly, so we're going to have to break this equation right here down into a series of first order differential equations. So if we have our first differential equation, let's call it x1 prime or something like that. And that one can be just equal to x2 prime, and then just equal to x2 directly. And then x2 prime can be equal to negative g. All right. And now if we think about our initial conditions, let's say that initially we're starting the ball off at x equals some x naught, and then dx naught is equal to 0, right? And so that should be all we need to go into MATLAB and begin trying to solve this problem. So before we jump straight into MATLAB, I want to show you the solver we'll be using for this problem. That's going to be ODE 45. ODE 45 is generally the first solver you'll go to for differential equations. It kind of handles the stuff that those of us who don't understand what the solvers are doing under the hood completely, it just kind of does it for us, right? So there are a number of other solvers that you should be to go to the bottom of this ODE 45 page. There's like a summary of all the ODE solvers and stuff like that, ODE 113, 23, whatever. Sometimes if ODE 45 isn't working, it's worth it to go try one of the other ones out. I can't fully explain to you why that works or doesn't. But anyhow, let's go ahead and hop on into MATLAB. So, create a new script and tell it to close all figures and clear everything when we get started. All right. And let's start off by defining our initial conditions, or why not. And we'll start it off at a value of 10, let's call it meters. And the initial velocity is 0. So remember, this is going to be your position and then your velocity in the y state, which would make the differential of y be your velocity and your acceleration, right? And so that's how we're getting the second order differential equation into MATLAB. Let's say our t naught, actually let's just go ahead and just call these y and t. We don't need to have the knots. T initially is 0, and we'll need that later. And then we can set gravity to whatever we want. Let's just put it at negative 9.8 right now, which would be standard for Earth, of course. But we want to make it kind of general. I want to show you how you can make things general, and so you could change this value later easily from outside. The next thing to do is to figure out the time span over which we want the solver to run. So let's just go 0 to 5 seconds. We're using meters and seconds, so this would be, we got meters per second right there, so this inherently is going to be seconds. And then let's go ahead and set up the function that's going to define how we take our differentials. So the way ODE45 works is we're going to need to give it a function that takes in the time and the position, or the state vector in this case, right? Because we've got two things, it's both position and velocity, and gives you back the differentials, in this case, velocity and acceleration. So we'll make that function right here inside, and we'll just call it, well, ball dynamics. How about that? That seems reasonable. And we'll tell it to take in t, y, that's again the state, and then we'll also let it take in g, so we can control it from outside. I'll get throw an end in there. So the first thing to do is we'll set up this dy dt. It's going to be a 0 matrix of dimension 2, 1. And then it's pretty simple. We know that dy dt is equal to, I'll put 2 equals there. So, I'm sorry, that's dy dt of 1. So the first thing, the velocity, is equal to the state vector, second element, which is also velocity. And then we know that the acceleration is equal to that value g that we're passing in. And that's all we need for that. So now we can come back up here and we can define our ODE function. So we'll say that our t and y we're going to get out will be equal to, well, let me make these y naught and t naught. All right. Will be equal to ODE 45, and we'll take, we're going to use this function down here that we define, this ball dynamics function, and we'll do that by using this little function handle button, which is the @ symbol. And then we've got this extra g right here, so we need to do something special. We need to do some binding. So we're going to say at t, y. So essentially what the ODE45 will see is a function that takes in two values, in this case t, y, and we're going to pass them in each time to the ball function with directly, and then we'll also pass in the g. And so what will happen is when this line is first run, it's going to make a new function that takes in two elements and bind that g value into the ball dynamics. So then the ODE45 function can continuously use this function over and over and over again as it solves the equations. Because it's doing a numerical solver, right? So it'll run this a bunch of times. We'll then pass in the time span that we're going to use. We'll pass in our initial values, and that should be it. And we can give that a go. So let's see what happens. Oh, I haven't saved it yet. All right, there we go. All right, and then what we can do is we can plot, I guess we can just put that in here. Can plot the values. So this t, as you can see, is 69 by 1, the y, 69 by 2. So we're just going to want, well, we can plot them both. So we're looking here at y, all the values in the first column, and we'll also plot all the values in the second column against t. And then we can also throw a legend in there. And so essentially the first one is going to be, the position, and the second one is the velocity, right? Because that's our state vector again coming back out. All right, let's give that a try. There we go. All right, so as you can see, we didn't actually, so we don't currently have any way to handle the bounce occurring. And so the first thing you might think to do is to come into this ball dynamics function right here, and you could have a statement in here that would be some sort of if statement. So maybe we'll try that. If y of, so if the first one, if the position is less than or equal to 0, and you need to check for the less than or equal to because this is numerical, it can go past the actual 0, right? It might not be exact. And we also want to see if the second one, so if it's still going down. So if it's already going up, then we don't need to do anything. And so if that's the case, then dy dt, so the first one, the velocity needs to be the absolute velocity. So essentially we'll make sure it's positive. And then else, we'll just do what we were doing before anyway. All right, we can give that a try. Let me reformat that real quick, just so it's a little bit cleaner. There we go. And we can give that a run. And what you'll notice right off the bat is that this is not running cleanly like it did last time. So if you look down here in the bottom corner, you can see it says it's busy. And it's actually going to stay busy for quite a while. Let's see if we can figure out why. So what we can do is we can come in here, we can kill it by hitting Control-C. And let's get some printouts. We'll just be kind of sloppy here, and we'll just say, we want to see all of dy dt. Let's see also t and y. And because I didn't put semicolons after those will print out each time. So we can see them. We can let that run for a little bit. Go ahead and pause it. See that t is 1.4307, and if we kind of go back, essentially just staying at that value. So if we go right below that, if we go like 1.43, then let's see what happens. We'll change our time span to 1.43 and run it again. And you can see this time it completed. And essentially what we'll see, if I grab this little crosshairs tool, and I can click right there. Well, let me just look at what the final value of y was. So let me look at, so the final value is 0. Essentially what's happening here is it's getting locked up when contact occurs when we change the direction in this way. That's happening because this numerical solver is seeing a rapid change in the differential, and what it thinks is it needs to drill down and have a smaller step size to find where that differential, it assumes it's smooth inside. And so it turns out you can't actually do this sort of change in direction in ODE45 or with any of the differential equation solvers that are numerical. So I have to find another way. And that other way is going to be to use events. And so what we can do, if I clean this up real quick, is we can tell the differential equation solver, ODE45, to look for a place where an event occurs. And let me close that out real quick. I think I got something on events over here. So the way that works is you create this event function. The event function takes in the values t and y from the ODE solver, and then it's going to put out a value, and what that value is something that can cross 0 essentially. And so it's looking for the ODE solver will look for when value crosses 0. If it crosses 0, you tell it whether this is a event that you want to stop on, or this is an event that you don't want to stop on. So 1 would be stop, 0 would be don't. And then also which direction you want to catch the event from. So whether it's coming from both directions 0, if you put a positive value in there, then it's only if the value is increasing. So for like -5, -4, -3, -2, -1, 0, 1, then it would catch that, but not the other direction. And then -1 would be the converse, so if it's decreasing. And so what we can do is we can stop the ODE solver from executing each time the ball hits the ground, change the velocity, pass it back in as an initial condition, because remember we're using that entire state vector with the velocity and the acceleration, and we can take that back around and add that on to our total calculations, and we can get a nice solution for the ball bouncing. So let's take a look at how we do that. So the first thing that's we're going to have to do is we're going to have to set up an options thing. So you can't pass it directly into ODE45, you have to pass in this option structure, and you set up that using ODE set, and we'll say that we have this new event, and we haven't defined it yet, but we're going to create a function that is ground impact. Okay. And then before we forget, we need to increase this t-span back out to be something long enough that we make sure it'll actually hit the ground. So we'll put that back at 5. We know that at that point it will always hit the ground for what we're doing. And let's go ahead and down here and define this this function. And so those outputs, those 3 outputs we were talking about, we'll put right into here. So there'll be the position, right? Because we're just looking for when position crosses 0. That is terminal, which we know is going to always be true because we want to stop. And then the direction, which we're going to only look for if it's decreasing, not if it's increasing. And we'll call the function ground impact as we noted up there. And it takes in those values that are defined, the t and y. We'll go ahead and put an end on that. So position is equal to the first element in y, right? And then is terminal is true, so let's stop when we hit that. And then direction is only if it's decreasing. Great. So now this should all be set up here. We need to pass in that options value to the ODE 45, so we pass that in right there. And let's just see what it does right now if we run it like this. So you can see it got right to where it collided with the ground, and then that's it. That's what we would expect, but we want to get that next bit, so we want to get the bounce. So what we can do is we can put all this stuff into a for loop. So if we do for, and we can do a number of bounces, let's say we want to do 10 bounces. And all we really want to do is solve for the ODE. So inside here we have to be a little bit clever with what the initial y0 or y0 is, right? So y0 will be correct the way we have it set up right now for the first time, but then for every subsequent time it won't be. So we're going to come in here, we're going to redefine these as y and t, and we'll say that y0 is the last value, the last row in t. Okay, and so y0 equals y of end comma all, right? So that'll be the last row. So if we take a look at what y looks like right now, we've got all these things. We can test what that looks like. So end comma all. Perfect. That's exactly what we're looking for. Okay. So that's done. And then we need to think about what we want the velocity to look like, right? So actually this y0 needs to be right. So then we also need to pass in for y0. So this got it. This y0 still has this negative value, right, for velocity. So we need to go ahead and redefine. Oops. Redefine that second value to be the absolute value. All right, so now that will ensure that that's becoming positive. And we need to think about what we want to do when this is actually running. So we're getting this new t and y out, right? And t will now be starting. Well, what we can do is actually we can redefine t span in here. I think we can do that. So t span equals, so if we take the final t, so we take t of end, and then we can do, all right, and that should be fine. So now we've got the right span, and then we just need to concatenate these things on up here. So let's redefine these so they don't overwrite everything to be t new, y underscore new. Why is this picture a fit? Okay. And then we'll say that we're going to concatenate t and, sorry, it's going like that. So this is not the most efficient way to do this sort of concatenation. It's not a big deal because of what we're doing right here, but if you wanted to run your code faster, you'd have to find a way to pre-allocate, or in reality what you would end up doing is you would end up making multiple dimensions, then taking those dimensions and kind of squishing them together later. All right, so now we've got all that. And there's something in here that it does not like. Huh. I'm not quite sure why it is upset. But let's go ahead and give it a run. Let's see if it breaks. Okay. So essentially I'm just missing this little brace right here, and all those arrows will go away. Let's give it another run. And now we can see that this plotted out pretty nicely. I'm not loving the way this is plotting. I'd rather see this position and velocity on separate plots. So we can do that, right? So we'll create a figure right here. And let's make it a subplot. So we'll do subplot of 2, 1, 1. And let's go ahead and plot the position first. Go ahead and grab that, put it up there. Now we can do the second one. Reformat all this stuff so it's not so messy. All right, and then we don't need that legend right there. Let's just see if that works real quick. Oh, forgot a parentheses right there. So now you can see we have the nice little subplots. Let's give those some titles. Oh, that's not horizontal, that's vertical. And I'll also add some labels to that so they actually are nice figures. So we'll do all right, let's try running that and see if that comes out. Cool. Except that I definitely flipped my labels there. Not a big deal. Fix that real quick. All right, so we had talked about getting pretty close to this. This looks good. The only thing that's missing is that the ball keeps bouncing at the same height each time. We talked about using a coefficient of restitution to clean that up. So let's add that in as well. And where that's going to go is right here in this, this place where we're defining the new velocity every impact. So let's just put our coefficient of restitution, and let's call that just 0.8. And actually, I tend to like to bring my stuff up here, however you spell that. So we'll grab that, put it right there. Let's try running it again. Now you can see the ball actually dies out, the velocities die out, and we've got a pretty cool little bouncing ball. So yeah, there you go. That's how you make, you can solve some differential equations. You can have impacts where the differentials are changing directions. You've got second orders, you can go to many orders. You could also extend that state vector to have not just the y direction, but also the x direction as well. And that could be, more informative. So now you have a ball bouncing in 2 dimensions, and so on and so forth. All right, the last thing I want to say is that